Hello, everyone. As Chris mentioned, my name is Jessica Sandberg. I'm a senior bridge engineer at Atkins and was responsible for the design of the River Dee and provided much of the site support as well during the construction. So basically, we're going to go through just what the scheme involved generally, how the structure was built and designed over the time and when it was eventually opened, a bit of a design overview, and particularly some of the design challenges that we had to deal with, particularly on the environmental grounds of this site, because it was quite a sensitive environmental area. And then going through some specific design and construction issues that we encountered during the project's running. The Aberdeen Western Peripheral Road and Balmedi to Tipperty is a DBFO scheme, so with basically it involves designing and constructing 58 kilometres worth of new dual carriageway between the southern part of Aberdeen up to Balmedi, and then extending it up to Tipperty in the north. This was to relieve congestion in the centre of Aberdeen itself and move the main traffic outside of Aberdeen through the bypass. It was funded by Transport Scotland and managed by Transport Scotland on behalf of the Scottish Government, together with Aberdeen Council and Aberdeenshire Council. The sort of operating commission is a 30-year commission that's managed through Balfour Beatty Investments, Galliford Try, and originally Carillion Private Finance, though that share has now been bought up by another company. The construction itself was then a construction joint venture between Balfour Beatty, Morrison, and Carillion. Because it was quite a big scheme, like 58 kilometres in all, and it was also a design joint venture between Atkins and CH2M Hill, which is now Jacobs. The structures were pretty much split equally between the different consultants and the contractors. So quite a large scheme in all. What I'm going to be concentrating on here is the River Dee crossing, which is located down to the southwest of Aberdeen. It's marked up on the slide here. So timeline of the design, the original tender was done back in May 2013, with detailed design being carried out between 2014 and 2015. There were still some ongoing design issues being carried out into mid-2017. This included a lot of the contractor supplied issues, such as the bearings, the post-tensioning systems, expansion joints, and things like that, the procurement of them hadn't been quite sorted out while we were doing the detailed design. So we had to continue the interface on that until those had been procured. Because as you can imagine, on a bridge of this size, some of these things are quite large and involve quite a lot of interface between designers, contractors, and suppliers. Construction of the bridge commenced in summer 2015, with quite a few difficulties encountered on site in the first couple of months, not helped by the fact that we had some major flooding on site over the Christmas of 2015 to 2016, which delayed things quite significantly. This project was then finished in November 2018, with the Dee open to traffic in late December 2018, and the whole scheme opened early 2015. The bridge itself consists of a continuous in situ post-tension concrete box girder, which was built by Balance Cantilever. The main span of the bridge was 120 metres with two 75-metre backspans, and it carries a dual two-lane carriageway over the top of it. And this means that we've got a total width of the structure of 27.6 metres. So it's a fairly significant width of bridge. This means there's also 270 metres long as well, so it's a fairly substantial structure. The Balance Cantilever method was used for the construction, where we used travelling formwork on 4 fronts during the construction to enable the program to be met. And the segment widths varied between 2.5 to 3.5 meters. This structure was wholly designed by Atkins, and it was Cat 3 checked by Fairhurst. As you can probably imagine, with a structure of this size and width, we had a fair number of tendons involved in trying to support it during the construction and permanent design. So at the sort of in the top cantilever tendons, we had 64 tendons with 31 strands in them, and the continuity tendons over the midspan, which proved to be the most difficult area to design on this structure. We also had a significant number of tendons sitting in there, with 42 27-strand continuity tendons sitting there. The back spans contained a bit less than that because they were a bit easier to design, and the stresses back there were far smaller than the rest of it. Because it is quite a heavy structure, to manage the compression stresses within the structure, we used C50-60 concrete to manage the stresses within the structure and the relatively small cross-section size compared to the overall length and width of the structure. One thing that was included that was pretty unique to this structure was a 1.5 meter high H4A containment parapet with a transparent noise barrier system incorporated within it. The reason for including this was to minimize the overall width of the structure, as using two separate systems would have meant adding an additional 1 meter width onto either side of the structure, which would have made the design slightly more challenging than it already was. So this meant both less concrete and less post-tensioning required in the overall scheme of things. When we started off, this H4A barrier combined system wasn't CE marked, so that added to an additional thing that had to be dealt with during this design process. Some of the key design challenges of the River Dee Bridge was due to the environmental constraints. These environmental constraints were due to the River Dee being classified as a special area of conservation, and meant that there were certain areas within the Dee boundaries that we weren't allowed to conduct any construction within, and we weren't allowed to have any of the permanent structure encroaching within this as well. This is what actually determined the span length of the bridge, because we had to locate the foundations outside of the special area of conservation. And it also determined the construction methodology that had to be adopted, because no construction activities were allowed within the central area of the river and within the banks of the river as well. Key things that led to this special area of conservation being designated are things like the presence of freshwater mussels, where the River Dee is one of the key sites for maintaining this mussel population. It's also got a large presence of Atlantic salmon, which use the river, and then it's got a large population of otters as well, using the riverbanks, which is why there's such a large width of river bank that is sort of designated for the otter use. That and the fact that the river is prone to flooding as well, which we found out to our detriment in the first year of construction, when everything flooded, including all the construction equipment, which meant some quite interesting delays being encountered. These environmental constraints also led to other constraints being adopted on the structure, including having quite a slender deck structure, due to trying to minimizing the height of the embankments on the approaches and allowing sufficient clearance above the river and sufficient clearance on either side of the river. We actually ended up with a fairly small cross section for a bridge of this size, and particularly this width. And this led to a number of design issues during the detailed design process due to small width of flanges that we had and the sort of overall width of the bridge and the weight of the whole structure. We also then had to deal with the sort of constraints of the construction side of things. So we had the travelling formwork was not able to deal with weights above 250 tons. So all the segments had to be designed so that they met the 250 ton limit as to not overload the travelling formwork. Then also because of the size of the structure, we had quite a number of interface issues between the designers and the suppliers of the travelling formwork, things like the bearings, which proved quite challenging to procure and get tested and fit within the geometrical constraints that we had for the structure as well. We also had the usual problem of the contractor wanting to come up with the most efficient construction method for doing various things. So we had to deal with the constant design changes from the contracting side of things as well as the already challenging conditions of the structure. So things that we had to consider in the design were things like the out of balance cantilever scenarios. We had to consider the intended out of balance condition because the segments would not be poured at the same time, so they had to be allowed to pour one side and another side. So that was allowed for within the design, including the weight of the travelling formwork as well, because again that could be moved on one side before it was moved on the other. And then were things like material imbalance of the concrete being potentially slightly heavier on one side than the other side, and this was all allowed for as well. On top of that, things like transverse out of balance wind were also allowed for. And at one stage, we were quite concerned about dynamic effects from the wind as well, because we had quite a long cantilever exposed over the river that was a bit prone to wind. But eventually, we managed to determine that dynamic effects weren't really a problem. On top of the designed out of balance condition, we also had to design for that accidental out of balance condition, and this was again done in accordance with the accidental load combination Eurocode Nord, where the same sort of out of balance assumptions were made as for the intended out of balance condition, but also allowing for the immediate loss of our concrete section. And we included a 1.5 dynamic impact factor for that, based on stuff that we'd found in literature. To support the bridge during the construction phases, we had some temporary props on either side of the structure. This is because we had bearings at the pier, so the pier couldn't be fixed to the superstructure. So we needed something in addition to this to allow the structure to be supported during the temporary case. These temporary props consisted of concrete props together with the sand jack system. And this was deemed to be the most cost-efficient way of doing it by the contractor during the design. And here are some images of the cantilever travelling formwork. This is during one of the concrete pours. And it also gives you an indication of exactly how large this structure actually is. And here's some more pictures of the bridge whilst being constructed over the river. And as you can see, there's some quite big loads sitting at the cantilever side of it that were then considered within the design of the whole thing. We also had some interesting design issues encountered due to the small size of pile caps and things, because as I mentioned earlier, we were not allowed to construct anything within the special area of conservation around the river. And this meant that the pile cap size had to be minimized as much as possible. So for the Dee Bridge, we had a pile cap at either of the piers of just 12.3 by 8.2 meters. And we had a 3 by 5 pile grid, which meant 15 piles supporting this, and the piles were 1.65 meters in diameter. These piles had to resist some rather large out of balance design moments, plus the loads that would be imparted on it during the permanent condition as well. Basically what this meant is that we had to design for an awful lot of reinforcement to go into a very small space. Well, this was something that was discussed in a lot of detail with the contractor to work out exactly what would make the most efficient way for them to construct it. And it was agreed that we would design the whole thing by strut and tie models, which would allow us to place all the main reinforcement between the piles. This meant that we had some very heavily congested areas of reinforcement between the piles because we only had about 1.5 meter spacing between the piles once all the pile positions and reinforcement had been located. So this meant that we ended up with 4 layers of B40s between the piles in the longitudinal direction and 3 layers in the transverse direction of B40s, and these were located at 90 mil centers, so very highly congested areas. But by doing that, it meant that the amount of reinforcement that we had going through the piles themselves was reduced to B25 bars at 150 mil centers, which was a lot easier for the contractor to place given the uncertainty involved with where the reinforcement positions actually ended up being. And it also meant that we could allow lapping of the 25 mil bars within the piles, which again helped them position the bars and meant that we could actually get all the reinforcement in. All the planning that we actually did during the initial stages of design did mean that it was actually quite straightforward, not easy to get the piles built. So we ended up with quite similar problems with the piers. And again, strut and tie analysis became our friend in here because we were dealing with some very high loading coming into the piers through the bearings. And we were dealing with the highly congested pile caps reinforcement having to be threaded into the piers as well, which meant close spacings being required in the piers as well as the pile caps. But it meant we could use smaller bars that then gave us a bit more flexibility as the construction progressed. And again, we had quite a lot of challenges trying to design the top area of the piers for the bursting stresses, particularly due to the curved geometry of the piers and this profiled cutout that we had on the edges, which was there for aesthetic purposes. So this then is a picture of the final piers in position, the central pier in position with a special iron oxide concrete mix, which gave it it's a grey colour to match the local granite. And then we've got the concrete pot rocks together with the sand jack sitting on top of them. The deck design, similarly, quite a lot of challenges involved with that. Again, primarily designed through strut and tie analysis. If you can say nothing else about this job, it meant that we really learned to push the strut and tie methodology to its very limits. Just about everything had a strut and tie analysis attached to it. And again, we had fairly high strength concrete here, C50-60, with an early strength gain of 40 newtons per millimeter within the first 3 days. In some cases, we actually achieved this in 36 hours to allow early stressing, which was quite important during the construction on site because we had a 7-day turnaround period between one segment and the next segment. And having very rapidly gaining strength concrete was absolutely critical in order to meet that timeline. To determine that we had the correct concrete strength by the time they stressed the concrete, we used temperature matched cubes for the concrete. On top of the other challenges that we had for the deck, we also had a 600 millimeter diameter water pipe that had to run through the entire length of the bridge, which meant that we had a couple of interesting holes that had to be put into the diaphragms to allow for this, in addition to the normal access holes that you would need in order to maintain the bridge. And then here some more pictures of the diaphragm area as it was being constructed. At the hammerhead, it was constructed in 3 different stages, with the bottom flange cast first, followed by the webs and the diaphragms, and then the top flange. And then this is some more pictures of the diaphragm while it was being cast. And then that's the pier hammerhead section in its initial position. And then installing the travelling formwork within the structure. The deck design itself was carried out using RM Bridge, which was used to look at the overall design and loads in the structure. Each of the tendons was modelled and detailed within the structure, and the gross section properties were used, allowing for shear lag, given that both top and bottom flanges were quite wide. Shear lag became quite an important aspect of the whole thing. What we found to be the most challenging part of the design was the design of the tendons themselves within the section. Because of the overall width of the structure of 27.6 meters, and the bottom flange being significantly less than this, varying between 8 and 12.4 meters, and a fairly small span to depth ratio with 2.5 meters deck at the midspan and 6.5 at the piers. This basically meant that we did not have a lot of cross-section to work with throughout the design, and therefore to manage all the stresses that we had during the permanent case, we ended up with a lot of tendons in the bottom flange. To try to manage that, the bottom flange being shown in the bottom image on this page, we, instead of having the traditional, more S-shaped tendon arrangement, where you allow a straight perpendicular anchorage point to the deck, we had to have curved tendons, which meant that each of the anchorages were angled relative to the deck. And this did lead to some issues during the construction of the deck, because we were trying to keep the tendons as close to the webs as possible to avoid putting undue stress onto the bottom flanges. And this meant that in some instances we actually had to change the stressing sequence of the continuity tendons during the construction, because the construction tolerances meant that we couldn't actually fit jacks into the intended area. But luckily we did. There was always space on at least one side of the bridge deck, so we ended up just tweaking the arrangement of the stressing position, and that meant that eventually we managed to get all the tendons in, and in the most efficient arrangement. I seem to be missing a couple of pictures on this slide. But basically, because of the size of the structure, the varying cross-sections and everything else, it was quite a challenge to present the design information in a clear and succinct way. To manage this, we basically produced a series of tables to present all the reinforcement and all the tendon arrangements in a tabular format. And this basically meant that over the 40-odd segments that we had on the bridge, we ended up with about less than 20 drawings outlining all the tendon arrangements and all the reinforcement arrangements throughout the bridge. And this was particularly useful when we had to make last-minute changes in the design, because the tabular format very much lent itself towards managing change in a very effective way. And the feedback from site was that it worked very well for the contractor as well, which was quite useful, because it meant that they had far less drawings they had to manage on site compared to what you would have had to do if each individual segment was detailed on its own. Oh, that's where the drawings went. So that's the final picture of the River Dee construction during the continuity tendon stressing. This then just talks about what I was mentioning earlier, that we had some very close interfaces with the contractor throughout to manage the constructability of the whole thing, particularly where we had very congested areas of reinforcement. So this close interface meant that when they actually got to site, all these things like access into reinforcement cages and similar was very well managed, and they didn't really have any significant problems with assembling the reinforcement. So it all worked rather well in the end. So that's the last slide from me showing the River Dee construction in a fly overview. Thank you everyone for listening.